All right, let's just jump right in. For as long as we've been human, we've told stories to make sense of the world, right? Myths, legends, sacred texts. But what if the greatest story, the most epic, mind-blowing tale of them all, isn't one that was written down thousands of years ago, but one we're still uncovering piece by piece through science? That's the idea we're digging into today, guided by the work of physicist Lawrence Krauss. Krauss throws down a challenge right from the start. He makes the case that the story of our universe, the one we've discovered through reason and experiment, is just fundamentally more awe-inspiring than any ancient text. It's a story where we are the detectives, figuring out the cosmos for ourselves. So the big question is he right? Have we found something even greater? Well, let's find out. All right, first up, Beyond the Shadows. Our story really begins where all great stories do, with a journey out of the dark. This first part is all about humanity's slow, often difficult, climb out of the shadows of ignorance and into the light of real understanding. You know, we've always had this deep-seated feeling that there's more to the world than what we see. For some, that's the dream of a fantasy world, a magical land hidden in a wardrobe. But there's another kind of hidden world, the one scientists are after. It's the underlying reality, the hidden machinery of the cosmos that explains why things work the way they do. This isn't a quest for fantasy, it's a quest for fundamental truth. And the perfect way to think about this is Plato's famous allegory of the cave. Imagine you have these prisoners who have been chained their entire lives, forced to stare at a wall. Behind them, there's a fire, and things are passing in front of it, casting shadows on the wall. To them, these flickering, two-dimensional shapes are reality. That's it. They have no clue, absolutely no idea, that they're just seeing a pale imitation of a much richer, three-dimensional world. So think about it from their perspective. What would they even make of this? Just looking at the shadows, they'd see things that randomly stretch, shrink, and change direction. Their world would seem totally chaotic, completely unpredictable, with no consistent rules whatsoever. A concept like length would be meaningless. But what happens if one of them breaks free? If they escape the cave? They'd see the truth. And this is just a brilliant analogy for what science is. All that confusing, chaotic behavior on the wall was just the projection of one simple, predictable thing, a spinning weather vane. Science is the act of escaping that cave, turning around and seeing the simple, beautiful reality that's causing all the confusing shadows on the wall. So, who were our first heroes on this journey? Who were the first to really start escaping the cave? This next chapter is about the pioneers who started to see the hidden connections between the forces of nature. And our first hero is a guy you just have to love, Michael Faraday. He starts out as a bookbinder's apprentice. No formal education, just this raw, unstoppable curiosity. His story is just this amazing testament to the power of asking questions. You see, Faraday didn't think in complicated equations. He thought in pictures. He imagined these invisible forces, like electricity and magnetism, as fields, lines of force filling all of space. This idea that space isn't empty, but filled with these invisible forces, well, that was a total game changer. And then along comes James Clerk Maxwell. He took Faraday's beautiful pictures and translated them into the rock-solid language of mathematics. And what his equations showed was just mind-blowing. They showed that a changing electric field creates a magnetic field, and a changing magnetic field creates an electric one. They create this self-perpetuating wave that travels at, wait for it, the speed of light. And just like that, bam, electricity, magnetism, and light were all revealed to be different faces of the exact same thing. An absolutely huge moment. But you know how it goes. Solving one great mystery often creates a new one. And this incredible unification, as amazing as it was, created a massive headache for physics. It set up a direct conflict between two perfect theories, which brings our next hero to the stage. Okay, so here's the problem in a nutshell. On one hand, you've got Galileo's principle of relativity, which says the laws of physics should work the same for everyone, no matter how fast you're moving. Makes sense. On the other hand, Maxwell's equations said the speed of light is always the same. Always. But how can both be true? Look, if you're on a train going 50 miles per hour and throw a ball forward at 10, someone on the ground sees it going 60. Simple. But with light, it doesn't work that way. If you turn on a flashlight, both you on the train and the person on the ground measure that beam of light moving at the exact same speed. How on earth is that possible? This is where Einstein comes in. And his real genius wasn't about tearing everything down. It was his incredible intellectual courage to say, wait a minute, Both of these ideas are backed by solid experiments. They both have to be true, somehow. He refused to pick one over the other. So he asks this beautifully simple yet world-changing question. If the speed of light is the one unbreakable rule of the universe, the one thing that never, ever changes, what part of our reality, what part of our common sense has to be wrong? What has to give? And the answer, oh man, the answer turned everything upside down. It wasn't the laws of physics that were wrong. It was our most basic, fundamental ideas about reality. To make it all work, Einstein realized that space and time themselves have to be flexible. They can stretch, they can shrink. There's no such thing as a universal clock or a universal now. This leads to some seriously weird stuff, like the car in the garage paradox. Imagine a car that's too long for a garage. If it drives fast enough, a person standing still would see it shrink and, for a moment, fit inside. But to the driver, the garage is the thing that shrinks, so the car could never fit. The paradox is, who's right? They can't both be, can they? Well, from the perspective of the person standing still, watching the garage, it's pretty straightforward. The car is moving super fast, so it actually gets shorter. It zips in, and for a split second, both doors can be shut. It fits. Simple as that. No problem. But for the driver, the garage is the thing that's comically short. So how do we solve this? Well, the key is a single word: simultaneity. You see, the driver and the garage owner don't agree on what happens at the same time. The driver actually sees the back door of the garage open before the front door closes. So from their point of view, the car is never fully trapped. The crazy part? Both of them are right in their own reference frames. Okay, so just as physicists were getting their heads around a universe where space and time are bendy, a whole new rabbit hole opened up. The story now dives from the cosmic scale of relativity down to the bizarre, counterintuitive world of the very, very small, quantum mechanics. Max Planck, one of the pioneers of this new field, said his big breakthrough was an act of despair. And that just perfectly sums up the vibe of the quantum revolution. The experiments were showing a world that just didn't make sense. A world where particles could be in two places at once. It was so weird that scientists had to literally throw out their most fundamental beliefs about reality just to make sense of the data. So after decades of this mind-bending work, we ended up with something called the Standard Model of Particle Physics. It's basically our grand theory of all the known particles and forces, a masterpiece of human intellect. But for a long, long time, it had a hole in it, a crucial missing piece, a crown jewel that no one could find. And to find that final piece, we built this, the Large Hadron Collider. And the scale of this thing is just hard to even comprehend. We're talking a 27-kilometer tunnel colder than the vacuum of space, smashing particles together 600 million times every single second. It is one of the most magnificent and complex machines ever built by humankind, all to find one tiny elusive particle. And then came the day, July 4th, 2012. The announcement came from CERN. They had found it, the Higgs boson, the particle responsible for giving other fundamental particles mass. This was it. The final piece of the puzzle clicked into place. It was the triumphant end to a 50-year-long quest. But here's the beautiful thing about this story. Finding the Higgs wasn't the end. It wasn't closing the book. It was finishing an incredible chapter that just opens up a whole new volume of questions and mysteries. And that's really the point, isn't it? The story of science, unlike the stories of old, is never finished. It's a living, breathing epic that we're all a part of. We've discovered that the universe in all its vastness is understandable, and that realization, that might just be our single greatest accomplishment. And the best part? The most exciting chapters are the ones that haven't even been written yet.